So, welcome back again. Good day, and we start the day after we had talked about the combination of cells, internal resistance, discussed about EMF and the cells, etc. Now we start the day. I take up an example from a textbook. Well, there is a network or circuit. Whenever there is a little bit of complexity in the circuits, they are called networks. So our network, it starts from A, goes to B, to C, to D. And between A and B we have two resistors which are in parallel, 4 ohm, 4 ohm. Then there is 1 ohm resistor over here, and there is a parallel combination of 12 and 6 ohms to the point D. Okay, and this is now connected. This network between the points A and B is connected to a battery. A battery which has an EMF of 16 volts and internal resistance 1 ohm. Okay. So this is the description of the network. Now there are three questions. Okay. Compute the equivalent resistance or equivalent, and then obtain resistance in each resistor, this, and also find VAB, VBC, VCD. What is the distribution of potential drops? Okay. Now I have put in a current which is coming out of the positive terminal of the battery I, and which comes back here I. So this is over here it will be I, over here it will be I, and over here it will be I. And as I said, I is equal to Y. Okay, so this is the situation. It's very simple. It's very easy. Okay. Now, what I have done is, I have redrawn this network over here. And this is what is my advice also to you, because you have the pen, you have the paper, and you can scribble fast. So I am redrawing it not like this. This topology I have just changed to this one. Okay, from A to B, one path, another path, both 4 ohms. From B to C, 1 ohm resistor is there. Even if not writing ohms over here, everywhere, saving our time. Okay, like I am writing an exam, multiple choice type question, and then this one 1 ohm, 12 ohms and 6, I have just exchanged the positions just to show to you that it does not matter at all. Okay, as long as the series and the parallel paths are depicted, there is no problem in that. Okay, now let me compute the resistance between the points A and B. So from the formula, R1 R2 upon R1 plus R2, product upon sum, turns out to be equal to 2 ohms. There is no calculation involved here, 1 ohm, and here it is 6 into 12 upon 6 plus 12. In fact, this is something which we should remember. Okay, for example, if I have 24 and 12, this will turn out to be 8. Okay, if it is 3 and this is 6, then it will turn out to be 2, less than even the least. So this I have shown as the equivalent resistor over here made a drawing. Okay. So 1, 2 plus 1 plus 4 gives us 7 ohms as the equivalent resistor, which I am written ohms over here, is no problem. Now, the current I will write. I have combined these two together. Okay. I is equal to 16 upon 7 plus small r. The internal resistance, which is equal to 1, so 16 upon 8 will give you 2 amperes. So I have been able to compute the value of I. Goes like this, here, 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 everywhere. Even within the cell. Okay. Flowing from the negative to the positive of the cell or the battery. Natural flow. Okay. Natural. Next, I try to find out as to, so the current is 2 amperes. VAB between A and B. The total resistance has been 2 ohms. Okay. So I will calculate this as VAB equal to 2 ohms into 2 amperes, which is 4 volt. So between this and this, there is 4 volts, and when I divide this 4 volt, which appears here also and here also, so in the first case I have 4 volts divided by 4 ohms is equal to 1 ampere, and similarly 4 equal to, I have shown it here. So I have been able to say as to what is the value I1 and what is the value I2. They turn out to be the same because of the numerical values involved. Okay. VBC. Between B and C, the current is I, which is 2 amperes, multiplied by 1 ohm, and you will find, okay, 2 volts. So 4 volts and 2 volts. Similarly, VCD, which is, I find that the net resistance over here is 4 ohms multiplied 2 amperes, it turns out to be 8 volts. Okay. Now, I designate this current as I3, I4, I can do it I12 and I6, etc. The symbols don't mean there anything. And like I have shown here 4 volts, I will show 8 volts over here. No need to write plus and minus, because we always understand that this is a fall of voltage. Okay. Like that. So I3 will be equal to 8 volts divided by 12 ohms, 2 by 3 amperes, and I4 will become equal to 8 volts divided by 6 ohms, 4 by 3 amperes, and then we check back I3 per I4 turns out to be equal to I. And similar kind of a check you can put in this case also, that I1 plus I2 is equal to I. So it appears to be something difficult, but it's very, very simple kind of a calculation that we have just done. Similar kind of calculations we can do with whatever numerical values we give to resistances like that. There can be other this 1 ohm also can be a parallel combination of 3 resistors or 4 resistors, no problem. We can do that. Okay. So we have learned that, and we will be able to do that. So after the solution of the problem that we have taken, let's revisit the parallel combination of cells. Okay. So we draw 2 cells in parallel between the points A and C. E1, R1 and E2, R2. Where I have taken the points P1 and P2 for the sake of potential. Okay. And you can see that the current I1 leaves from here and current I2 leaves from here, from the positive terminal of the battery, okay, and enter into the negative terminal of the battery as it is. This is the equivalent where I have ER and the current is equal to I exiting and also I entering. Now, the terminal voltage I can write as V is equal to VB1 minus VB2. Okay. So, VB1 minus VB2. If we come like this will be equal to E1 minus IR1, which gives I1 is equal to E1 minus V upon R1, and E2 minus I2R2, it gives I2 is equal to E2 minus V divided by R2. Okay. Now the key thing is that I is equal to I1 plus I2. Okay. So I can write this, substitute these values over here, that this is equal to E1 minus V upon R1 plus E2 minus V upon R2. And I separate the terms. So E1 upon R1 plus E2 upon R2 minus I take V as common. So this is 1 upon R1 plus 1 upon R2 in bracket. Okay. So this, if I take the LCM here, R1 R2, so this will become equal to E1 R2 plus E2 R1 divided by R1 R2 minus V R2 plus R1 into R1 R2. Okay. Now if I rearrange the terms, I can write capital V as equal to, I take it on this side, I will come on this side. So I can write this as equal to E1 R2 plus E2 R1 upon R1 plus R2. Okay. And minus I into R1 R2 upon R1 R2. Okay. Now let's write the equation for V from the equivalent circuit. This will turn out to be equal to V is equal to E minus Ri. Okay. Now if we compare these two equations, then we find that E is equal to this thing and R is equal to this thing. So I can write a set of equations here that E is equal to E1 R2 plus E2 R1 divided by R1 plus R2 and R1 R2 upon R1 plus R2. Okay. Now what we do is we simply divide E by R. If we do so, then this R1 plus R2 and R1 plus R2 that cancels out, and what I will get is E1 R2 plus E2 R1 divided by R1 R2, okay, which is obtained, which I can write as E1 upon R1 plus E2 upon R2. So this is the result that we obtained for the exercise. E upon R is equal to E1 upon R1 plus E2 upon R2. Okay. So I can write, and of course the resistance R is the combi of these things. Okay. So in general, E upon R will be equal to E1 upon R1 plus E2 upon R2 plus E3 upon R3 plus and so on plus En upon Rn. And 1 upon R will be equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3, etc., etc. So this is what we obtain for the case of the parallel combination of cells. Okay. So we stop here. Okay, and in the next outing we'll talk about something, but actually what we have to talk to you about is KVL and KCL. KVL and KCL, K stands for Kirchhoff's voltage law and Kirchhoff's current law, which is nothing but the conservation of charge and the conservation of energy. I will introduce that, and we'll do some problems relating to circuits, and maybe solve some combinations of resistances, etc. So, thank you very much.